Now example 1, y is equal to m sine inverse x, then prove 1 minus x square y double dash minus x y dash minus m square y. So let's solve it. The given is y is equal to e raised to power m sine inverse x. Let it be equation number 1. Now differentiating with respect to x, we get y1 is equal to e raised to the power m sine inverse x using chain rule multiplied by m into 1 upon differential of sine inverse x 1 upon under root 1 minus x square. Now we have to transpose this to left hand side, so we have 1 minus x square y1 is equal to m e raised to the power m sine inverse x. Now this is equal to y, so we have to replace it here by y. So it becomes under root 1 minus x square y1 is equal to my. Now squaring both sides, we get 1 minus x square within bracket y1 square is equal to m square y square. Now differentiating with respect to x, we get using product rule 1 minus x square as it is differential of y1 square, which is 2y1 into y2 plus differential of first function minus 2x and y1 square as second function as it is equal to m square is constant coefficient and differential of y square by chain rule 2y into y1. Now dividing both sides, by 2y1, we get 1 minus x square y2 minus x y1 is equal to m square y. Now transposing m square y to left hand side, we get 1 minus x square y2 minus x y1 minus m square y is equal to 0, and this condition we needed to prove. So we have proved the given required condition this way. Now example 2, log y is equal to tan inverse x. Prove that 1 plus x square y2 plus 2x minus 1 y1 is equal to 0. So we have taken the given condition log y is equal to tan inverse x. It implies that y is equal to e raised to the power tan inverse x. Let it be equation number 1. And now differentiating with respect to x, we get y1 is equal to, using chain rule, we have to differentiate e raised to power tan inverse x. So differential is e raised to power tan inverse x multiplied by differential of tan inverse x 1 upon 1 plus x square. Now transposing 1 plus x square to left hand side, it goes in the numerator, so we get 1 plus x square y1 is equal to e raised to the power tan inverse x, which is exactly equal to y by equation number 1. So we may replace e raised to power tan inverse x by y. So we get 1 plus x square y1 is equal to y. Now differentiating equation number 2 with respect to x, we get, using product rule, first function 1 plus x square as it is and differential of y1 is y2 plus differential of first function is 2x, second function as y1 as it is equal to the differential of y on the right hand side, that is y1. Now transposing y1 to left hand side, we get 1 plus x square y2 plus 2x y1 minus y1 is equal to 0. Now we get 1 plus x square y2, and taking y1 out of these two terms common, we get 2x minus 1 y1 is equal to 0, and this is the condition to be proved. So we have proved the required condition. Now example 3, if x is equal to sine 1 upon a log y, prove that 1 minus x square y2 minus x y1 minus a square y is equal to 0. So given x is equal to sine 1 upon a log y, it implies that transposing sine to left hand side, we get sine inverse x is equal to 1 upon a log y. So it implies that a sine inverse x is equal to log y, which may also be written as log y is equal to a sine inverse x. It implies that y is equal to e raised to the power a sine inverse x. Let it be equation number 1. So now differentiating equation number 1 with respect to x, we get y1 is equal to, using chain rule, differentiating e raised to the power a sine inverse x, we get e raised to the power a sine inverse x multiplied by a upon under root 1 minus x square. It implies that transposing under root 1 minus x square to left hand side, we get under root 1 minus x square y1 is equal to a e raised to the power a sine inverse x. As we know, y is equal to e raised to the power a sine inverse x, so we may replace e raised to the power a sine inverse x by y in this equation. So we get under root 1 minus x square y1 is equal to ay. Now squaring both sides, we get 1 minus x square y1 square is equal to a square y square. Now differentiating with respect to x, we get first function 1 minus x square as it is, differential of second function, that is 1 by 1 square, whose differential is 2y1 into y2, plus differential of first function, that is minus 2x, and second function y1 square as it is equal to a square is constant coefficient as it is, and differential of y square is equal to 2y by 1. So dividing both sides by 2y1, we get 1 minus x square y2 minus x y1 is equal to a square y, or 1 minus x square y2 minus xy1 transposing a square y to left hand side, we get minus a square y is equal to 0. So this is the condition to be proved, and we have proved the required condition. Now by mistake I have written example number 5 rather than example number 4. So here we have to prove d2y upon dx square is equal to minus b for b raised to the power 4 upon a square y cube, where x is given as a sin theta, sec theta, y is given as b tan theta. So we have taken x is equal to a sec theta as equation number 1, y is equal to b tan theta as equation number 2. Then we are going to differentiate 1 and 2 with respect to x. So differentiating 1, we get dx upon d theta is equal to a sec theta tan theta, and let it be equation number 3. Now we are going to differentiate equation number 2 with respect to theta, so we get dy upon d theta is equal to b, differential of tan theta is sec square theta, so b sec square theta. Let it be equation number 4. Now dividing equation number 4 by 3 to find dy upon dx, dividing 4 by equation 3, we get dy upon d theta upon dx upon d theta is equal to b sec square theta upon a sec theta tan theta. Now here 1 power of sec theta can be cancelled from numerator. So we get b sec theta in the numerator, and in denominator a tan theta. Now we may write it as b 1 upon cos theta, because sec is the reciprocal of cos, and in denominator a sin theta upon cos theta in place of tan theta. So cos theta is cancelled by cos theta from numerator and denominator, and we get b in the numerator and a sin theta in denominator. So we may write it as b upon a cos sec theta, because reciprocal of sine is cos sec. So on the left hand side, as we know, dy upon d theta upon dx upon d theta is equal to dy upon dx. So on the left hand side we get dy upon dx, and on the right hand side we get b upon a cos sec theta. Now differentiating the above equation with respect to x, we get on the left hand side d2y upon dx square is equal to, on right hand side, b upon a, and differential of cosec theta with respect to x we need to use chain rules. So minus cosec theta into cot theta into d theta upon dx. Now as we know, the value of dx upon d theta is a sec theta tan theta, and here we have the reciprocal of dx upon d theta, so we may write it as minus b upon a cosec theta into 1 upon a sec theta into tan theta. So we get minus b upon a square, because in denominator we have two a's, and cosec theta, which is the reciprocal of sine, so we may write it as 1 upon sine theta, and cot theta may be written as cos theta upon sine theta, into 1 upon cos theta may be written as cos theta, and 1 upon tan theta may be written as cos theta upon sine theta. So multiplying all these terms, we get minus b upon a square. In the numerator we have cos into cos into cos, cos cube theta, cos cube theta. In denominator we have sine into sine into sine, which may be written as sine cube theta. So ultimately we have minus b upon a square, cos cube theta upon sine cube theta may be written as cot cube theta, or 1 upon tan cube theta. Now as we know from equation number 2, we have y is equal to b tan theta, so tan theta is equal to y upon b. If we substitute this value of tan theta in this equation, we have minus b upon a square into 1 upon y cube upon b cube. So this b cube goes in the main numerator because this is the denominator of denominator. So as per rule, it goes in main numerator, and we get d2y upon dx square is equal to minus b was already there and b cube goes in numerator. So we get b raised to power 4 in numerator, in denominator a square y cube. So this is the condition to be proved, and we have proved it.